Okay, so we're back and we're going to start with the histology of compact bone. And hopefully this is a review from lab. You've already had this in lab. But remember that the osteon is going to be the structural unit, the kind of building unit of compact bone. And it's also called the Haversian system because it was first discovered by the British physician Clopton Havers. So I always like when they kind of keep the old name, giving credit to the first person that discovered it. So you'll hear it called osteon, but you'll also hear it called Haversian system by some of us old schoolers. I can't believe I'm calling myself an old schooler there, so again, these are the structural units of compact bone. They consist of these kind of concentric rings, remember, of lamellae. And the lamellae are actually they look like these annual tree rings, right? These are actually rings of matrix. So that's what the lamellae are, rings of calcified matrix. And then they're going to surround this central canal where the blood vessels and nerves are going to run. And so that's what makes up our osteon. And the reason that we have, again, these osteon bone forming units, and I think this might help you understand why we have the osteons, is if you think about the fact that you have to transfer nutrients to all of these osteocytes. All these osteocytes are living cells, right? So they need nutrients coming from these blood vessels through the central canal. So you can only go so far away from that central canal before you need another bone forming unit, right? Because these cells are at the kind of back end of getting nutrients from that central canal. So you can only go out so far. So then you need another bone forming unit here with another central canal to feed those cells. So that's why you end up having these osteons in your compact bone. Okay, and remember that our osteocytes are going to be found in, I'm going to just kind of fast forward here. Oh, and then really quick, I also wanted to talk about the fact that the osteons end up being these long cylinders that run the entire length of the bone, that compact bone, and they end up acting as these kind of tiny weight-bearing pillars. And what's really cool is that if you look at the collagen fibers in the lamellae, these rings of matrix, they actually run in different directions in adjacent rings. So, they'll run this direction in this ring, and then the next ring, they'll run the opposite direction. And then the next ring or next lamellae, it'll run in the opposite direction. So each kind of adjacent lamella will have collagen fibers running in the opposite direction. And this really helps that osteon withstand stress, as well as it helps it to resist twisting. So it helps it to resist twisting forces. So I always think that's pretty cool. That's it's built in, right, to your osteon bone forming units, this natural, again, built-in way to protect our bones from, stress and twisting. So always pretty cool when you see some of this stuff. And then remember that in that matrix, you've got bone salts that are going to be found between the collagen fibers, and that's what makes up that matrix. Okay, so when we talk about, again, the microscopic anatomy of these osteons, we're going to see these central canals, right, that are running through the core. They're going to have the central or Haversian canal. Again, I still call them Haversian canals, but central canal or Haversian canal, either one, I'll use both on the test. Or where you're going to have all the blood vessels and the nerve fibers running, right, in the center of that osteon. And then you also have these things called Volkmann's canals, or again, perforating canals. I'll use both. Volkmann was, again, the scientist that originally discovered these canals. And these canals are going to run at right angles to the central canal, and they'll run from one osteon to the next. Okay, so our central canals, again, are going to be in the center of these osteons, carrying blood vessels and nerves, lymphatics, okay, in the center of those osteons. And then you have the Volkmann canals, or perforating canals, that are going to run in between. So, and again, I love this image. you can kind of keep going back to this image because I feel like it really gives you the big picture. So here again, you have, some type of long bone, and then, they've done a cross section here through the diaphysis, through the shaft. So you can see all of the different layers. You can see the periosteum, again, that layer of connective tissue on the outside. Remember, peri means around, osteum or osteo would mean bone. So this is that connective tissue layer that surrounds around bone. So you've got your periosteum. You can see all of your osteons, those bone-forming unit. They break them down and they show you those concentric lamellae. You can see here you have your actual osteocytes here. And so I like this drawing here because you can actually see the lacuna, which is the space that the osteocyte is trapped in. Remember, as it secretes matrix, and that matrix calcifies, it's trapped in this space called the lacuna. So here's your osteocyte. And then these osteocytes, again, have to have a way to be able to transport nutrients from one osteocyte to the next, as well as a way to communicate from each other. So they have these canals and extensions off of these osteocytes called canaliculi. And so here you can see, these osteocytes, as they transfer nutrients from one osteocyte to the next, they'll do it through these canaliculi. So here, this cell will gather nutrients and things from that central canal, from the blood vessels from the central canal, and then it will pass them on to this osteocyte through the canaliculi, and then this osteocyte will pass them on to this osteocyte through the canaliculi, and so on. So again, and that's just a fun word to say, canaliculi, right? So that's what those canaliculi are, these canals, these extensions coming off of those osteocytes that are used for communication and, again, transferring nutrients from osteocyte to osteocyte. So this is kind of nice because this is actually a slide of cross-section through bone, and you can see, again, these osteons here. So this would be like an osteon. Actually, let's see if I can turn on my pen real quick for you here. And so here you can see, this here would be an osteon here. Oops, if I can draw this right. Okay. And then here would be another osteon. Okay. And then you can see here, this would be the central canal, and then you've got these lamellae, right? These rings of matrix. So here's the lamellae here, and then here, and then you can see, and I'm not drawing the whole ring obviously around here, but the ring around of matrix. So that's your lamellae, lamella, again, singular, lamellae being plural. And then here you have the lacunas with your osteocytes in them. And then these little things are the canaliculi, okay? So again, kind of nice when you can kind of put that all together and see that microscopic anatomy. So, and just as a reminder that it's originally the osteoblasts that are going to secrete the bone matrix. And then what ends up happening is as those osteoblasts surround themselves with bone matrix, and that bone matrix calcifies, then that osteoblast gets the signal to mature to an osteocyte. And so then it's called an osteocyte at that point. And so I think, yeah, and again, the canaliculi allow communication between those osteocytes and permit sharing of nutrients and waste. So we've talked about that a couple times. And again, this just kind of shows you another view of compact bone here. And then you can see the spongy bone towards the inside. And this is nice because, again, you can see the periosteum on the outside, and then the endosteum, endo would be inside, right? So the endosteum is actually going to line the bony canals of the spongy bone that are going to be lining the medullary cavity. Okay, so this will be the medullary cavity here. Okay. So hopefully, again, if you're struggling with that, please set up some time with me and I can go over this with you, so that way then we can make sense of it for you. Okay, so when we talk about spongy bone is going to look very different. And spongy bone does not have true osteons. So it does have, a similar arrangement to the osteons, but you'll notice that there is no central canal here, right? So because there's no central canal, it's not a true osteon. And so we call them something different. So what ends up happening is you have these kind of circular arrangements of bone forming, and then this one here will kind of join up with this one here, and this one here will join up with this one here. And what ends up happening is it forms this kind of lattice work instead of that compact bone where they're all dense and up against each other. Forms this lattice work of kind of these thin plates of bone that we call trabeculae. Okay. And so it's going to leave spaces in between these kind of the lattice or struts of bone here. And these spaces here are actually going to be filled with red marrow. So we typically find our spongy bone in the ends of long bones, as well as inside the flat bones of, like, remember your hip bones. Remember we talked about your sternum, and that's why, again, you've got that spongy bone in there with the marrow, the red marrow. So again, you can do a marrow draw from the sternum, and then the sides of the skull, as well as the ribs. So again, a couple of areas where you're going to find that. And again, this is what it's going to look like. You remember that spongy bone will actually be sandwiched between these two thin layers of compact bone. So this is where I talk about the sandwich, right? Look for these flat bones. And this spongy bone that's in these flat bones, it has a special name called diploe. So just kind of as a reminder there. And when we talk about bone, remember, keep in mind that bone is very vascular. So this is actually the reason that bones actually often heal. If you're to break a bone, it actually heals faster than if you do it, the sprained ankle or something like that. Because again, anytime that you're damaging or tearing a tendon or a ligament, because those are not very vascular, they take a long time to heal. So again, remember that dense regular connective tissue really isn't very vascular, and it takes quite a long time to heal. So believe it or not, oftentimes a minor break actually heals faster than a sprain. So you can see why it's very vascular, right? When you're looking at this bone here. And when you talk about especially long bones, you're going to see that you have a number of different arteries. You're going to have the periosteal arteries here, which are going to serve the periosteum, again, that layer of connective tissue surrounding the bone. Then you're going to have this large artery that's going to supply the diaphysis. So we call it the nutrient artery, which kind of makes sense. It's bringing in nutrients, if you want to think of that, to the diaphysis, the shaft. So it's going to enter through this large foramen. Remember, foraмен's an opening that we call the nutrient foramen. And again, this is going to supply the compact bone in the diaphysis, as well as provide the red marrow, again, to some of that spongy bone that's going to line the medullary cavity. And then you have your metaphyseal and your epiphyseal arteries. So remember your metaphysis here is going to be in between the diaphysis, your shaft, and then your epiphyses here. So you're going to have your metaphyseal arteries coming in for that to, again, supply nutrients to that area. And then you'll have your epiphyseal arteries coming in to supply the epiphyses. So let's get into bone formation now. And when we talk about bone formation, all embryonic connective tissue is going to begin as these special stem cells that we call mesenchyme cells. Okay. And so again, mesenchyme is just a term it's a word that you'll have to get used to. And all it is a fancy word for basically these stem cells that are going to eventually differentiate into all the different types of connective tissue. So again, these are stem cells that are going to rise to maybe dense connective tissue, maybe loose connective tissue. Again, they could be cartilage or again, bone. So that's what those think of those mesenchyme cells as connective tissue stem cells. And bone formation has the fancy name, of course, osteogenesis. So genesis being kind of like the beginning of our birth of, and then osteobone. So that's the term that we use for bone formation more formally in anatomy. And there are actually two types of processes for bone formation. So we have basically two types of ossification that can occur. We have what's called intramembranous ossification. And intramembranous ossification, oops, my computer blipped there, so hopefully you guys got that. But intramembranous ossification is going to be the formation of bone within, right? So that's intra means kind of within or between connective tissue membranes. That's where the membranous comes from. Okay? And then the other type of ossification is going to be called endochondral ossification. And again, endo is going to be within, inside of, and then chondra is going to be cartilage. So this is going to be the formation of bone within, from inside of what's called a hyaline cartilage model. So there's just two very different types of ossification that can occur. So the very first one that we're going to talk about is we're going to start with intramembranous ossification. And intramembranous ossification is going to form the flat bones of the skull. It's going to form the bones of the mandible as well as your collarbone or clavicle. So those are a couple of places that you'll see intramembranous ossification. Again, intramembranous ossification is just the process of how those bones basically became bone. So what ends up happening, and I'm going to go through the steps. These are the actual steps of it, but I'm going to actually use, because I'm a visual person, I'm going to actually use this diagram and this diagram here to kind of go over the different steps. So the first step for this is basically an ossification center is going to form from originally what was mesenchymal cells. And these mesenchymal cells at some point get a signal to actually become an osteoblast. Because remember, again, these are stem cells that can get signals to become any type of connective tissue. So they're going to get a signal to become an osteoblast. And remember, osteoblasts will secrete that osteoid matrix, that bone that will eventually calcify and be the bone matrix, right? So that's what's happening here. Okay, so first we have these mesenchymal cells, they differentiate into these osteoblasts, and then these osteoblasts start to secrete that osteoid matrix. Okay, now as that matrix again surrounds, it eventually surrounds the cells and starts to calcify. So that's our next step, calcification. Then it will trap those osteoblasts, right, in their lacuna. And then now those osteoblasts will basically be signaled to mature and become osteocytes. Okay, so now these are osteocytes. And so that's step two. Now the third step in the process is that the calcifying matrix centers, okay, that you have here. So you have, an ossification center here. So that one might be, maybe that one's right here, okay? And then you have another ossification center maybe right here, and then another one that's forming right here. And eventually these ossification centers are going to join to form the bridges that become the trabeculae, okay? So again, another one might form here. And so that's the third step, is the formation of the trabeculae as these ossification centers kind of join up. And then what ends up happening is you can see on the periphery here, the mesenchyme cells that are, so here you can see the mesenchyme cells those stem cells are just kind of sporadic here. But here, those mesenchyme cells really start to condense. And as those mesenchyme cells in the periphery condense, they're going to develop into what's called the periosteum. Okay, and then so you'll see on the outside here, you have this periosteum, so you still have these mesenchyme cells, which is important because, again, we're going to talk about things like bone remodeling, where you're constantly kind of making bone and then breaking bone down. And we'll get to that a little bit later in the lecture. But so it's important to understand that you still have these mesenchyme cells in the periosteum. And then you still have these osteoblasts as well, right? That are lining the outside here in the very kind of inner layer of the periosteum. And so it's important to remember that because those osteoblasts in the periphery are really important for, again, bone remodeling, or if you break a bone for, right, bone healing, because they can secrete bone matrix. So again, hopefully that kind of puts all this together for you. There is a great little YouTube video here that has an animation of this intramembranous ossification. But again, it's forming in these kind of fibrous connective tissue membranes, which is how it gets its name. So, and this is just, again, another kind of step-by-step diagram that talks you through the same thing. Again, ossification centers appear within that fibrous connective tissue membrane. Again, these mesenchyme cells, as they differentiate into osteoblasts, they're going to secrete the matrix, and then that matrix is going to calcify, trapping these cells in the lacunae. They become osteocytes. And then here again, those ossification centers start to join together, forming the trabeculae. Then we'll have, the invasion, of course, of blood vessels into this area. We didn't talk about that in the last model, but you'll start to see the invasion of blood vessels coming in here to feed, of course, those osteocytes, as well as, again, to fill the red marrow in the spaces in that spongy bone as well. And so that's kind of your last step here. Again, the red marrow appears. And then you'll see that some of that kind of woven spongy bone on the outside of the periphery near the periosteum will actually end up being replaced by compact bone here, just again on the outsides there. So again, that's and that is what is going to end up forming, again, those nice flat bones of the skull with that sandwich effect. So again, that last step where this actually ends up, again, that spongy bone becomes compact bone just on the periphery there, forms that sandwich effect that we talked about. Okay, so when we talk about, again, that I like this diagram here because it kind of shows you where intramembranous in purple, intramembranous ossification happens. So again, in the bony place of the skull and the mandible, and then in the clavicles. And then everywhere else, right, all the other bones are going to be this other type of ossification called endochondral ossification. So again, the majority of the bones are going to undergo ossification through this process. And this, again, remember, is just involving the replacement of cartilage by bone. So we have a cartilage model that will be replaced by bone as the ossification process occurs. And so the very first step, of course, in this model is going to be the development of the cartilage model, okay? So we have to have the formation of the cartilage model. So, and again, we already talked about all bones except for the flat bones of the face, most of the cranial bones, and the clavicles, collarbones, again, are going to be this endochondral ossification. Only those are the intramembranous. And again, we start with this hyaline cartilage model. Oh, I hadn't talked about the fact that this typically happens around week 9 of embryonic development. So this process, endochondral ossification, again, happens around in the 2nd month of human development. And then it will continue all the way until early adulthood. Basically, the end of adolescence is when your growth plates will close. And so again, just like before, I do have this kind of whole process written out for you step by step. But of course, I like to go to the, sorry, it takes me a minute to get through this, but I like to go ahead and go through to the diagram. And then you guys can always refer back to my kind of step-by-step process here. So I'm just going to skip ahead here. Sorry, to this diagram. And I really like this diagram because it actually shows you around when each of these stages occurs. So in the very first stage of endochondral ossification, we have to have the actual development of the cartilage model. So we are going to end up having these mesenchymal cells, right, or stem cells, that are going to develop into chondroblasts. And those chondroblasts are going to form this cartilage model here. And then, of course, it will end up, that hyaline cartilage will continue to grow. That growth occurs by cell division of those chondrocytes. And then, so then our kind of first step here is going to be the development of this kind of primary ossification center, as well as this formation of this bone collar. So the bone collar is basically going to happen when these blood vessels are going to kind of infiltrate the perichondrium, which is going to be the outer layer of connective tissue, right? For the cartilage model, we call it perichondrium when it's cartilage. And the mesenchymal cells of this perichondrium are then going to actually specialize and become osteoblasts, so differentiate into osteoblasts. And those osteoblasts here will, of course, then start secreting matrix. And as they secrete the matrix, they will start to form this bone collar and form what's called the periosteum, right, on the outside. So basically, that perichondrium becomes periosteum. Okay? And again, we secrete the osteoid matrix from those osteoblasts, and that forms this bone collar going around what will eventually be the diaphysis of the bone. But again, at this stage, it's still the hyaline cartilage model. Okay, so then we have step 2 here. And so that in this step here, we have in this center, in this kind of what's going to become the primary ossification center here, we end up having this area of cartilage that deteriorates. And the reason being is that the formation of this bone collar ends up actually kind of reducing the diffusion of nutrients to the cartilage, because remember, cartilage isn't vascular like bone is, and so it relies on diffusion. So what ends up happening is the formation of this bone collar reduces the diffusion to the cartilage in the center here, and it deprives it of nutrients, and that cartilage just starts to deteriorate. And then what happens then is blood vessels really start to invade now. So this is what we call the periosteal bud, which will eventually become the nutrient foramen and the nutrient artery. But that blood vessel that from that periosteal bud that ends up becoming the nutrient artery invades this internal cavity, and where that cartilage was deteriorating, it's actually going to form spongy bone. Okay, so as we bring in blood vessels, again, these mesenchymal cells will then differentiate to osteoblasts in the center here, and then again, secrete matrix and form spongy bone. So then here, as this diaphysis continues to, in the next phase, elongate. And so again, we're kind of moving through these phases. This is happening at about month 2. Here, this phase happens at about month 3 in utero. And then right around birth, And the diaphysis is going to continue, obviously, to elongate during this time period. But right around birth, we're going to see the formation of these secondary ossification centers. Oh, and really quick, we have the formation of the medullary cavity as that diaphysis elongates, where originally that cartilage deteriorated. Again, it ended up forming this nice cavity that ended up becoming the medullary cavity. And again, the blood vessels could then continue to run through that medullary cavity, supplying again blood to these osteoblast cells, right? As the mesenchymal cells became osteoblasts. So then these secondary ossification centers occur in the epiphyses, okay? And so again, that happens right around birth. And now we have an ossification center here and an ossification center here. And now what will end up happening is the diaphysis here will kind of continue to elongate, and then these secondary basically ossification centers will become the epiphyses, and they'll end up becoming invaded with these epiphyseal blood vessels that will again continue the ossification process in the epiphyses. And so what ends up happening is then when completed, we're going to end up with just 2 areas where hyaline cartilage remains, okay? And that's from childhood to adolescence. And so you'll see there will be a layer. So as secondary ossification, the secondary ossification center, again, kind of expands, it will end up leaving just a kind of thin layer here of articular cartilage, hyaline cartilage on the outside, and then a layer of hyaline cartilage on the outside of this epiphyses. And that's, again, going to form the articular cartilage. Remember, when we talk about articulating, that's going to be, again, where 2 bones are going to meet up at a joint. And so that articular cartilage is actually going to help prevent damage to the epiphyses, right? Because this is an area, again, where it's forming a joint and there'll be friction in that joint as the bones move. So that's where we have that articular cartilage. And then the second place that a little bit of cartilage will remain is in these epiphyseal plates. So here's the epiphyseal plate, and here's an epiphyseal plate. And so you'll see that there'll be a bit of hyaline cartilage that will remain, and that's basically our growth plate. And that epiphyseal plate, that cartilage, is very important because that's the only way that the bone can elongate. And we'll talk about the lengthening of the bone in that process that occurs in just a minute, because that's a whole other set of other pathway that occurs. But once again, once you hit the end of adolescence and early adulthood, what will happen is this epiphyseal plate will eventually close up, completely ossify, and when that happens, we'll call this actually the epiphyseal line. So again, that will happen at the end of adolescence. That epiphyseal plate will officially close. Okay, so again, if you need clarification on this process, please, again, come see me, and I know you can't come see me in person, but I'll set up a time with you and we can always go over this. Okay, so for our next kind of series of slides, oh, and also you can go to this that same YouTube video that I had linked to before, and it's really cool because it goes through exactly what we talked about and has an animation of intramembranous ossification, and then the second part of it is the animation of the endochondrial ossification, so you can kind of compare the two. So this is a really great video, and again, it's only like 8 minutes long or something like that, so it's well worth your time. So now we're going to talk about, again, we talked about endochondral ossification up through, kind of birth, and then we talked a little bit about what's going to happen kind of through adolescence. So now we're going to get into the nitty-gritties of how that happens. So postnatal bone growth is going to be what we're going to and we're primarily going to talk about kind of the interstitial growth, the lengthwise growth. But postnatal bone growth, again, after you're born, you're going to have these two forms of growth. And one is called interstitial growth, and that's basically just the growth of a long bone in length. Okay, so again, long bones grow lengthwise by this whole special process that we call interstitial growth that we're going to talk about. This growth will happen at the epiphyseal plate cartilage, and it will happen as that epiphyseal plate cartilage grows and then is replaced by bone. So we're going to talk about that whole process here in just a minute. Okay, now bones also have to grow in thickness, and they do this through a process that we call appositional growth. And appositional growth will actually happen throughout your lifetime. So where here, you know, your interstitial growth is just going to be again up until your epiphyseal plate closes, again, after adolescence. So, but appositional growth can grow throughout your lifetime, and we'll talk about the fact that this is oftentimes stimulated by, you know, weight-bearing exercises and things like that. And so it's important to remember that, because this is the way in which you can kind of strengthen your bones after puberty. So we'll talk about that again as we kind of get into it too as well. Now, again, bones stop growing with interstitial growth, right, at the end of adolescence, but there are a few bones that continue to grow slowly throughout your life. So some facial bones, like your nose and in your lower jaw, will actually continue to grow slowly throughout your life. Kind of interesting. Not something that I'm going to test you on, but just kind of interesting. But again, most bones interstitial growth will stop after adolescence. We'll talk about that. Okay, so let's talk about this bone growth in length, this interstitial growth, okay? And this interstitial growth is going to happen at these epiphyseal or, again, epiphyseal plate or epiphyseal plates. Both, you'll hear both pronunciations. I use kind of epiphyseal plate. And that is, again, this kind of layer of cartilage. We call it the growth plate. And what's going to happen is these cartilage cells are going to continue to grow by mitosis on the epiphyseal side. So here you can see, here's your epiphyseal plate, right? Oops, I'm not doing a very good job of drawing it, but we'll pretend like that's your epiphyseal plate there. And so on the epiphysis side here, the epiphyseal side, this side right here, you're going to see these cells are going to be these cartilage cells that are going to be undergoing mitosis. So these cells are undergoing mitosis, okay, and pushing up. And on the diaphyseal side, that's going to be this side right here. Okay, so again, here's your diaphyseal side. These cartilage cells are actually being replaced by bone. So as this side here, on the epiphyseal side, the cartilage cells are undergoing mitosis and pushing up. On this side, behind it, on the kind of trailing side of the growth plate, here you have the cartilage cells being replaced by bone cells. So again, the rate of the cartilage growth on one side is usually equal to the bone replacement on the diaphyseal side. So the epiphyseal plate basically remains about the same, you know, in thickness, constant in thickness throughout, again, you know, its growth period. And the epiphyseal plate will typically eventually close, and we'll talk about the fact that how that does that in terms of, again, ossification kind of catches up. So basically, we'll talk about, you know, your cartilage cells will kind of slow their growth due to some input of hormones, different changes in hormones at the end of adolescence. And then what happens is this ossification side here will catch up to that cartilage side, and eventually that epiphyseal plate will completely close. And that will be at about around 18 to 25. Typically younger in females, we'll talk about that, and a little bit later in life in males. And usually by age 25, your interstitial growth, your growth in length is stopped. Okay, so we're going to talk about the epiphyseal plate, these different zones, and what's happening in these different zones. So if you were to look at the actual epiphyseal plate, this tiny little area here, and look at it microscopically and break it down, you can break it down into basically these 5 different zones. And again, we of course create these 5 different zones so that we can talk about what's happening in each zone. So here, this zone, this is on the epiphyse side. So this is the epiphyse that I'm going to put an E. And then here, I'm going to put a line here. This would be down below here would be the diaphysis, okay? Just to give you kind of an orientation of where you're at. So, and here's your epiphyseal plate. So if you look here, we'll break it up into these 5 different stages. Here would be what's called the resting zone or quiescent zone. This is going to be a zone of proliferating cartilage or proliferation growth zone. And then you'll have the zone of basically hypertrophy or hypertrophic zone of cartilage. And so we'll talk about what's happening here. And then we'll talk about, then we have the zone of calcified cartilage, and that's our calcification zone, and then our ossification osteogenic zone. Okay, so when we talk about each of these different stages, we just break this down for our purposes in terms of understanding what is happening in each of these phases. So when we talk about these different phases, again, the resting zone will be on that epiphyseal side of the epiphyseal plate, okay? So on that kind of periphery, and this is kind of a relatively inactive zone. Not a lot's happening here, and that's because its main job is just to attach the epiphyses to the rest of the bone. So it's basically attaching the epiphyseal plate to the epiphyses. The next zone here is the proliferation zone, and this is where we have cells of cartilage that are rapidly undergoing mitosis. So this is where we talked about the cartilage cells growing, right, and pushing up. So these cells divide quickly, and they're pushing the epiphyses away from the diaphysis, right, as these cells undergo mitosis and push up. Okay, and so oftentimes this proliferation zone, I feel like it looks like stacked coins when you look at it. And so that's kind of what's happening in that proliferation zone. And again, this is really kind of ultimately, eventually lengthening the entire bone, right? As it's pushing the epiphyses away from the diaphysis. So this is really what that proliferation zone is, what's going to cause that lengthening, okay? Then we have what's called the hypertrophic zone. And this is just where we have these kind of older chondrocytes that are now going to be kind of closer towards the diaphysis. And they're going to start to enlarge. As you can see here, they get bigger. And that's what we call hypertrophy. Hypertrophy just means to enlarge, right? And so what ends up happening then is they end up with these large spaces and these large lacuna and the lacuna actually ends up getting larger, right, as they enlarge, and they start to erode. And as they erode, they leave these much larger spaces, as you can see here. So they're going to start to leave these really large spaces in between, okay? So basically, their lacunae just enlarge as these cells enlarge, and they erode and leave these really large spaces in between. So that's what's happening in the hypertrophic zone. Okay, old cartilage cells enlarge, and they leave these larger lacunae and larger spaces in between. So then in the calcification zone, in this zone, this is where the kind of surrounding cartilage matrix, so this matrix that's in these spaces here, is going to start to calcify. And the chondrocytes, as it does that, the chondrocytes are going to start to die because remember again, the chondrocytes aren't fed by blood vessels. They're just diffusing nutrients from one, chondrocyte to the next. So as the matrix starts to calcify around them, basically these chondrocytes are going to be deprived of nutrients and they're going to start to die, deteriorate and die. And when this happens, you end up with these kind of spicules. So they basically they end up leaving these kind of big spaces that we call these kind of long, slender spicules and they kind of look, I think, to me, they kind of look like, and I know your book describes them as like these like stalactites, right? That are tied to kind of the roof of a cave. They look like they're coming down in towards the diaphysis, right? And so what ends up happening is, these calcified kind of spicules here actually end up oops, sorry about that. I had a quick interruption. But so what ends up happening is in these calcified spicules, right, will kind of stick down into that epiphyses diaphysis kind of junction here. And what's going to end up happening is blood vessels will start to invade the cavity here. And as the blood vessels start to invade the cavity, remember that gives that signal oftentimes to some of those mesenchyme cells to actually become osteoblasts, right? And so these osteoblasts down here on that, again, close to the diaphyseal side here are going to start to deposit bone matrix, okay? And so, again, now you're kind of at that border of the calcification zone, again, where that matrix is kind of, again, some of that matrix, the cartilaginous matrix has kind of deteriorated or died off, and blood vessels have invaded. And as blood vessels invaded, we kind of enter the ossification zone. And that ossification zone is, again, where these osteoblasts are now going to be secreting that bony matrix in place of in these spaces, right, of where we used to have that cartilaginous matrix. So ultimately what will happen is the spicules that we have here are actually partly eroded by some osteoclasts. It gets a little more involved here, and then eventually they're covered with new bone by osteoblasts. So these osteoblasts that are depositing that bony matrix and ultimately replacing it with spongy bone here. And so what ends up happening is that medullary cavity enlarges as these spicules are kind of eroded, forming that medullary cavity with the spongy bones surrounding it. So again, the big picture here again is that here you have the kind of cartilaginous proliferation zone here at the epiphyses, and here at the diaphysis you have that ossification occurring where again now cartilage is being replaced with bony matrix. So pretty cool process again on how this all happens. Now the growth and the length of long bones, again, this will end near the end of adolescence, and then what ends up happening basically is the chondroblasts on the epiphyseal side, right, in the proliferation zone, basically will kind of get signals as hormones change to divide less often. And as that happens, basically the, ossification zone where now you have, cartilage being replaced by bone is going to eventually catch up to that epiphyseal side. And eventually all of that cartilage will then be turned to bone, ossified. So again, the epiphyseal plate will thin and then eventually is just completely replaced by bone. And we call that point the epiphyseal plate closure. That occurs when the epiphysis and the diaphysis completely fuse, as again, all of the cartilages from the epiphyseal plate is replaced with bone. So bone lengthening then ceases at that point, and this happens oftentimes, typically in females, it occurs around 18 years of age. Again, obviously, this is going to differ between individual to individual. And we'll talk about the fact that this has to do with estrogen. And then males, this occurs around 21 years of age. And so again, because of the production of estrogen in females, a higher production, as we enter adulthood, that is why we oftentimes females end up having those epiphyseal plates close earlier. Now, oppositional, again, growth, remember, can occur. That's the growth in girth can occur throughout the lifetime as necessary. We'll talk about the fact that, again, excessive like muscle activity or like weight bearing exercises where you're again putting weight on those bones and stressing those bones that way will actually stimulate that appositional growth, that growth in girth. And again, that's a way that we can help strengthen our bones as we get older. So appositional growth is pretty simple. I'm not going to go too involved into this, but basically appositional growth is going to only grow at the bone surface. So again, here it's going to be right at either the periosteum or the endosteum. And what's going to happen is these periosteal cells here. So in this case here, we're going to see these little periosteal ridges form. And the periosteal cells will actually differentiate into osteoblasts, because remember, again, you have mesenchymal cells here. And they're going to differentiate into osteoblasts. And as they differentiate into osteoblasts, they're going to form these bony little ridges here, as you can see it kind of pushing in. And then they'll eventually form a tunnel around some of these periosteal blood vessels that were running through the periosteum, and then form these kind of concentric lamellae, right? That will end up, again, laying down matrix in that concentric, those circles of matrix around that central canal, again, forming what will eventually become the osteon. So that's how, again, bone is kind of growing out in girth. Again, this is happening, at the periosteum or at the level of the, endosteum to allow it to grow in girth. So again, growing bones widen as they lengthen, obviously, through appositional growth. So again, even as your bones lengthen, obviously you don't want to keep these, really skinny bones throughout your life. So they're gonna grow in girth as well through that appositional growth. But the great part is that appositional growth grows throughout our life. There is no epiphyseal plate, right? So it can occur throughout life. And bones will thicken again in response to this increased stress from muscle activity or added weight. Any type of weight-bearing exercise will stimulate that appositional growth. So again, especially for women after you've hit menopause, they'll really encourage this weight-bearing exercise to help strengthen bones and prevent osteoporosis. So the osteoblasts, again, beneath the periosteum are going to secrete bony matrix on the external side. And then when we talk about bone remodeling, so osteoblasts are really going to be laying bone beneath the periosteum on that outside. And then osteoclasts will actually usually be removing bone on the endosteal surface. So on that internal, remember the endosteum is going to line like the medullary cavity. So your osteoclasts will usually remove bone from the endosteal surface, and osteoblasts will usually build bone from that periosteal surface. Again, you usually have more bone building than breaking down, providing these thicker, stronger bones that aren't too heavy. But again, this will change from individual to individual, and you can end up having things like osteoporosis if you're not building enough bone, and you're not, again, building bone, and more bone is breaking down than building, then you can end up with issues like osteoporosis. So there's lots of factors that can affect bone growth. So again, just simply adequate levels of minerals and vitamins. So obviously calcium is a pretty easy one, right? Because you need calcium to make that calcium phosphate, but also phosphorus is important to make that calcium phosphate, right? Because remember that we need that calcium phosphate to make that hydroxyapatite. So we need both calcium and phosphorus in our diets for that purposes. Also, vitamin C is really important. We're not going to get into it, but it's really important in collagen formation. So obviously to make those collagen strands that are such an important part of the bony matrix, we need vitamin C. And then vitamin A is actually really important for stimulating osteoblast activity. So again, just kind of some interesting facts about nutrients and those types of things and how they might affect bone growth. Also, sufficient levels of specific hormones. So let's talk about hormones and how hormones regulate bone growth. So obviously growth hormone itself, and we're not going to get too much into this because you'll get into this in the endocrine system, but I'm just going to kind of briefly introduce this and you'll get into more depth in the endocrine system. But growth hormone is obviously your big important hormone in stimulating epiphyseal plate activity in infancy as well as childhood. And we'll talk about some disorders that happen, some abnormalities that happen when you produce too much growth hormone. So thyroid hormone also happens to like kind of modulate some of the activities of the growth hormone, kind of ensuring that, you know, proper portions of growth hormone are released at the right times. So thyroid hormone is important for that. Testosterone in males and estrogen in females at puberty can promote kind of adolescent growth spurts. But the big thing is that estrogen will be a big stimulator for ending growth by inducing epiphyseal plate closure. So again, a big release of estrogen. And again, estrogen's produced in both males and females, just obviously, again, more in females, especially at puberty. And so again, that will really stimulate those epiphyseal plate closure in females. So you can see why that would happen more rapidly at puberty for females than males. And then excess or deficits of any of these hormones can cause abnormal skeletal growth. So let's talk about some of that. So some of these hormonal abnormalities that cause different conditions are, you can either have over or under secretion of human growth hormone. I actually know someone that has a daughter that has an issue with under secretion of human growth hormone and actually has to take injections of human growth hormone. But over secretion of human growth hormone during childhood can really have large effects as well. Large, no pun intended there, but and it can cause things, especially if you have like tumors on the pituitary glands that will kind of stimulate the oversecretion of human growth hormone. This can cause things like acromegaly. And in acromegaly, what ends up happening is you're still secreting lots of growth hormone again after puberty, but your epiphyseal plates are closed. So now after puberty, you just end up with appositional growth. And so you can see here that it causes these, you know, kind of really bones that are really large in girth. And so we call this condition acromegaly. And actually, Andre the Giant, if you remember, he had this condition due to a pituitary tumor. And then both men or women that lack estrogen receptors on their cells. So if you lack, remember, estrogen will stimulate the epiphyseal plate closure. So if you lack estrogen receptors on your cells, so your cells don't respond to that estrogen, you'll continue to grow in length. You'll continue to have interstitial growth throughout your life. And so you'll grow taller than normal. And so what ends up happening is you end up with individuals that become, the tallest man or tallest woman ever. So this is Robert Wadlow. And again, he had this basically this issue where he ended up, he never went through really true puberty and his growth plates never closed. And so he continued to have this interstitial growth. So again, just kind of interesting when you talk about some of these hormonal abnormalities. So I'm going to go ahead and stop here, and then we'll start up on the next lecture next time.